Righty, well, happy Tuesday. Again, we're slightly behind here. Apologies, but templates will be quick. We should be able to cover that on Thursday, no problem before break. So we'll finish talking about recursion today, looking at more backtracking recursion. Having lots of fun with that. Again, that's our next project was the checkers backtracking recursion project. So want to make sure we have a good feel for it. We'll do that today. In lecture, we'll do a lab exercise on backtracking recursion, and then you'll do your project on it. Should be a lot of fun. We can come back to templates when we get back on 311. I think should be fine for that. So we'll have time to work on it here as we go. Um, and then hopefully nothing for break. If you want to work on the project over break, great. If you want to pretend like it doesn't exist, forget it for a week. That's great too. Should have plenty of time to work on it, right? Because it's not going to be due until the following Thursday, the 13th, right? So we should be pretty good there. If you got questions, let me know. Always happy to help with that. Other than that, we're almost done with Zybooks, right? We got 13, 14, and 15. So the linked list stuff and tax and cues just is lecture notes, nothing super special, no reading for that out of Zybooks. Here we go. And we're getting close to our last project. We'll get to that on the 13th. We'll do our last one um, using linked lists. And this should be a lot of fun here. And then the group project we'll do is our last month of class, essentially. So from the 27th to the 24th, almost a whole month. Should be pretty good. And we'll talk about that when we get a little bit closer. So let me pull up our recursion bit here. So we have this maze solver we're working on that does backtracking recursion. So we said, okay, what is our base case? How do we know if we're done? Right? To be able to solve something with recursion, we have to know when we're done. Well, we're done if we reach the end. Okay, game over. We can stop. If we didn't reach the end, well, then now we need to try and get one step closer to the end. And I don't know if I'm going to get there or not. I don't know which way it is, but I'm just going to literally try every single possibility. That's what backtracking does. It says try it. If it doesn't work, undo, try the next thing. If it doesn't work, undo, try the next thing. If it doesn't work, undo, try the next thing. Right? So we just keep on trying these things here until we're done. So with the maze solver, we're able to find here one solution, right? We stopped at the end here. And then we said, okay, otherwise go do this thing. So if we go run it again with our maze solver, we should get one solution to the maze. And there is only one. But what if we had two solutions to the maze, right? What if I go and say, hey, let's open this one up here and say, maybe now there's two paths. We can see it, right? Obviously, it's easy for us to see, but bigger mazes and things might be a little tougher. Um, but backtracking recursion is not efficient because it tries literally every possibility. And at some point, we're going to do that Stack Overflow thing where the maze was just too big. So somewhere around like 30 by 30, I think 35 to 35, the maze is just too big and it won't be able to solve. But for small mazes, it's fine and it's not too big of a deal to run it here. But we're going to see now there's two solutions, right? Here was the first solution it found. Here was the other solution it found, right? This starting here. So I guess we need one extra print here, right? When we output these things, let's go back and print and then we'll just see out one more end line. There we go. Just give it a little bit of a space here. There we go. So here's one solution. Here's the other solution. Cool. So we're going to find every single possible solution, which is kind of cool, right? But if there's like 50 different solutions here, if I want to go and like really mess this thing up here and put a bunch of spaces in, it's going to get unwieldy pretty quickly here, right? Now we run it. I've got how many different ones here did I print? Right? Because it can go this path and go this path and go, it's not necessarily efficient paths. So it might be nice if we tracked efficient paths, right? So we can track how many steps we've taken here and see what is the most efficient solver here. So when we create our maze, then, right, we need to know how many steps we've gone, right? So we're going to add in another variable here. Let's add another private attribute here for an int for, I don't know, number of, I don't know, moves, right? Starts at 0. Oops. Should not set the value. So number of moves, and then our constructor should go set that. So my number of moves is 0, right? So every time I call solve, if I'm not at the end, I need to make a move, right? So I can take my number of moves plus plus here, okay? If I've solved it, now I know how many moves it is, right? So I need also then a int, this is my number of moves until solution, right? And we'll probably start that one off at 0 until we know otherwise as well. So let's go to the constructor, set that one to 0, right? And if we want the shortest possible solution. And I want to say, okay, hey, if my number of moves is less than the number of moves until solution, then my number of moves until the solution is my number of moves. Oops, number of moves until solution is my number of moves, right? And then I should print that one out. Well, maybe not even print that one, right? Maybe I can save a solution somewhere here, right? I want to print out the shortest solution. Maybe I need a string then for solution. And then, so instead of printing now, maybe we have this return a string. So we'll have a print. This gets a little bit ugly here. So let's have a string here. We'll call it print. I don't know, maybe toString is better. ToString here. And then instead of outputting this, we're going to take a string result, then starts off as nothing, and we're going to take that result, add to it here, and then our result will add an end line character. Result plus equals the space. What is that, a backslash n then? Right, it's a backslash n character. And then when we're done, we can return the result. Right, so we can save the particular maze, right? So that solution then, so instead of print, we don't want to print. We'll get back to that in a little bit. Where is it here? Where's our constructor? So our solution equals nothing until we know otherwise, right? It's just blank. If this one is less than, we can take our solution that is equal to a toString, right? And we don't need to see out anything. So eventually we're going to have stored the solution, right? We'll find the shortest one. So if we found a solution in 20 moves, but the shortest solution, right, number of moves until solution, the shortest number here is 10, I'm not going to save it. If I find something better than 10, I want to save it, right? If I find something better than 8, I want to save it. If I find something, right, I want to find the shortest possible one. So eventually, it's still going to try all the possibilities, but it's not going to print all 50 of them because that's just really ugly and messy. So we just want to save the shortest possible path here. So we're increasing our number of moves here. What we need to do, right, when we undid that step, we said, hey, that was a dead end. It was no good. We need to undo that move as well. Number of moves minus minus. Uncount that move, right? So we're counting the move and we're marking a breadcrumb here. This is changing the board. So we're tracking it. We're recursing and then we're undoing that move. So we're going to do something, recurse, undo, right? Do something, recurse, undo. So that's the pattern we're going to follow for this. So eventually then we can print out when we're all done here. So maybe this solution, that's really like a private one then, right? Let's see, maybe we'll print the solution or see out the solution. Let's do that and in that line. And then we can even add in here, you know, number of steps maybe, see out solved in shortest number of steps, the moves until solution moves. Right, so now when we run that, we should get, hey, here's the shortest possible solution. Uh-oh, 0 moves. 0 is a bad default here, isn't it? Because we're never less than 0. Probably should have started that at something bigger, right? 0 is a bad thing here. So maybe, I don't know, isn't it like int max or something here? Int max. Here, we'll start it at the largest number here. And it's sort of silly, but that guarantees we're always going to go down from there. Hey, now we found a solution in 8 moves, right? There's other solutions in 8 moves, but none of them less than 8 moves, right? So if we start putting walls back in, we will get other things here, but we can force and find a short solution that direction, right? So we go back to our maze and add in a couple other, let's add in the wall here, and when we have a wall here, maybe we move the end to here, right? And then we put in another wall over here or something, right? So we can go 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 2 possible solutions here. One should be shorter than the other, but now we're limited, right? Now we found one in 7 moves. So it is finding the shortest one here, right? If there's more than one, that's the same. It's okay. We're just going to pick whatever the first one was. Does that part make sense? So we're looking at it's doing something, it's recursing, and it's undoing that step. Right? That's the big piece here. So when we're solving our checkers game, right, we need to do the thing, which is jump over a piece, recurse, and then undo is unjump that piece, right? Put the board back to the way it was so I can try the next possible option here, right? The next direction. Because our maze solver says, okay, well, I tried going down. After I've tried that and I came all the way back, what happens if I go left? All right, I tried that as far as I can. What happens if I go right? This way we can find all the possible solutions because it tries everyone, right? These are not else ifs here. Just because you can go right doesn't mean we don't want to try going down or going left or going up, right? We want to try all single possibilities. We're exhausting all of our options here. So could be kind of fun. If you want, you can generate random mazes here and make it solve random mazes. Maybe you think that's fun. Maybe you don't think it's fun. That's okay. But we can go and do that if we wanted, right? So we can make this vector a vector of maze here and go generate random ones. So let's do the solve one here. Let's generate 45 random mazes. How about that? So let's write a little helper function for, let's do a single character here. So this is a maze space here. Then, so we know we'll know where a start is, we'll know what an end is here, but we need a wall or a space, right? So what sort of random chance do we want here? Right? We can say, hey, if my rand, and this one gives me, what does random give me? Is that a number between 0 and 1, or is this one that's just a big number and I have to modulus? I think it's a big number. Okay, so let's do modulus 2. So I'm either 0 or 1, right? 50-50 chance here. Should we do 50, or should we do less than that? Maybe a wall every 4. So if this one is 0, we're going to return a wall. Otherwise, we can return an open space, right? So we can generate random spaces here this way. And then we'll go make a vector of type char. We already have maze, right? So that's fine. So we'll solve it. I want to like clear this out here as we go. So let's do solve the maze here. And then we'll say maze equals vector of type char. Make a new one here, right? And then, I don't know, for int, this is my row index is 0, row index is less than, what, rand mod 10, maybe between 0 and 10, right? Some number of rows, maybe with like plus 1, because we need to have at least one row, right? Or I don't know, plus 4, so at least 4 rows, right? Up to 14 or something. And let's do 7, right? So this will give me 0 to 6, plus 4 should get me 4 to 10 here. So somewhere between 4 and 10 rows, right? And then for same idea here, and column index is 0. It's as long as we're between 4 and that here, right? Let's go do something. So before we add the column, row index plus plus. There we go. And then column index plus plus. So for every row, we're going to take my maze and we're going to push back a new vector of type char. Right, so it's empty. I can't spell column index, can I? Oh, I put 2 n's in column. That's not good. So rename that to, there we go, 1n. Once I've pushed that back, then I need to have this many number of random spaces, right? So I'm going to take my maze dot at the row index, push back a maze space, right? It's either a wall or empty, right? I don't know which one's which. It's just random here, right? And then eventually, when that one's all done, then I want to set, I don't know, maze dot at 0 equals a start, and maze dot at what I want, the maze dot size, right? So it should be the last index size minus 1, dot at maze dot. So this will be last row, and then I want the size of, I'm sorry, at, oh my goodness. That's obnoxious. All right, I just want the last one to be row and column, or the end here. All right, here's the, I don't know, int rows is maze dot size, and int columns is maze dot at rows. or at 0, right? Because it should be a nice rectangle here, dot size. Then my maze dot at rows -1 dot at columns -1 equals an end character, right? This way we're putting the last corner. So we're starting in the top corner, ending in the bottom corner here. So we'll put a bunch of random things in, put a start, put an end, and then we'll go back and we'll create the maze solver and we'll solve it. We'll go back, make a maze solver, and solve it. I guess we should start with that first then, right? Make the maze and then solve it. That way I get my solution. And really, this is maybe we'll print so my maze solver. When we solve, we can say if my number of moves, because we might not be able to solve these ones here. So number of moves of the solution is less than max int. Then we can do this one, right? Otherwise, see out, no solution found. Maybe do we still want to print it then? Maybe we still. Goodness, too many. Is it not? Did I just use int max? Oops, int max. There we go. I guess we can do that, right? We can just print out the toString here, right? See out toString. So we'll show what the maze is and say no solution was found. So we should be able to generate 45 random mazes here. Maybe we don't need 45 here. Maybe we'll just do like 10 of them to start. We should get 10 random mazes and see if they're solvable. Oh, we broke it. Invalid vector subscript. Uh-oh. Maze.at rows. Rows is 7, columns is 7. 7 minus 1, right? Isn't that? Should be a 6, right? 6 in columns. Right? Maze is 7 as each one of these. What is that? Size is 7 as well. Why didn't that work? Let's see. Unassigned index. We added the row, we added the space, right? It looks like we've got a space here, right? Maze. Isn't that doing that? Let's see. Maze. They all look good there. There's row 6. Oh, okay. We didn't do the same size here. This is not working here because we're different sizes for every column. We don't want that. We want this to be one time a random value, not for every column here. So we'll have, I don't know, int for rows. Let's do this then. Is this one, and then int for columns is this one here. Right, there we go. This will be a little bit nicer. This will be columns. That way it's the fixed number of columns every time. All right, that's what we broke here. No? Okay. Columns, oh, redefinition, uh-oh. Rows and columns. Oh, nice. Now we don't have to redefine it because we know how many it was. That works out even better. So I know what the value was. I don't have to go calculate it. Hey, all right. So we had one solution here in 13 moves and one solution here in 10 moves. Okay, looking good so far. So 8 mazes that weren't solvable. Oh, it's still thinking. Oops. There we go. Some of these took a lot of thinking here. That's right. Yeah, if there's a lot of open space, there's a lot of possibilities they're cycling through here to get to some of these solutions. There we go. That's fun. So let me stop that. So this is, we print this one out here. No solution found, maze. Let's do one more. I have too many. I print the solution. I already have a new line here, so I don't need to print this one there. And then that'll space them out a little better. No, I want one more in between. Okay, no. After every print, let's try that. I just want to space it a little bit nicer. There we go. So this maze, we had 13 moves. This maze, we solved in 10 moves. This next one must have a lot of open spaces here. That one, 10 moves. Yeah, lots of open spaces. I was fiddling around with them here. So again, you can see backtracking is not the most efficient, right? Because it's trying every single possibility. The more spaces we have, the slower it's going to be, and that's okay. It's not claiming to be the best maze solver here. Oh, all right. So maybe we should tweak it a little bit here. Let's go for our random maze space then. Where did this one go? Maze space. How about we go? We want less of these. Maybe a third chance for a wall. See if that goes any faster instead of a fourth of a chance. Hey, no, look at that. Now we found one with no solutions. There we go. Yeah, you couldn't get through here. No solution. Okay, so now we're getting a lot of no solutions. That one's solvable. No solutions. That one's solvable. That one's solvable. That one's solvable. 16 moves. There we go. It's pretty straightforward. Yeah, straight down the edge. Nice one. And no solutions. Sure. Again, we're just kind of playing with it. We should be able to toss out some mazes at it and see if they're solvable or not, and do these sorts of things here. But the logic was still the same for this, right? We're going to do something, we're going to recurse, and then we're going to undo that thing. It's the same idea with your checkers project. You're going to do the thing, recurse, undo the thing. That'll try all the possibilities as we go here. All right. I think that's actually pretty good. We could do another one, but we're going to do one in lab. So we'll practice the one in lab come lab time, and then we'll get into vectors on Thursday here. Though we're not jamming too much. I'm sorry, templates. I don't know why I said vector. We're going to get into templates on Thursday, the 27th. Then we should be good to go from there. Okay. All right. Awesome. Well, thanks. I will see you in lab tonight then.